and today I will tell you something that I have been concerned in the last year and a half, and this is based on work I've done in the last year, but also some very recent work that will appear on the archive tomorrow, we just submitted today. And what we are worried about is that how we make a careful comparison between different searches for WIMPs. And in this talk, in particular, we'll focus on collider and direct searches for WIMPs. And in particular, how do we put experimental limits in the same plane for the same theory? So we have the same theory, we want to compare how collider exclusion compares with the one from direct detection. What assumptions are once we put them in the same plane, and what is the proper way to do that? And this is important, of course, to exploit the complementarity among different WIMP searches, and it will be even more important the day we have a discovery when maybe we want to correlate different signals in different searches. So just to a brief introduction on WIMPs. So WIMPs are motivated dark matter particles, and they are very broadly defined nowadays, we can say. So they are stable particles with a mass between 1 GeV and 10 TeV, and an annihilation cross-section of a pair annihilation of two WIMPs going to an arbitrary standard model final state, which particular final state depends on the model. And the annihilation cross-section for this process here is roughly 1 picobar, which is the size of annihilation cross-section mediated by weak interactions. So the reason why there is so much excitement about these candidates is because they are motivated by the hierarchy problem. Many frameworks addressing the hierarchy problem have naturally a WIMP candidate almost for free. And then they are produced in the real universe through thermal freeze-out. So by the same annihilation I draw here in this diagram, this annihilation is what sets the relic abundance in the real universe. And if the cross-section is roughly 1 picobar, we are in the ballpark to recover the amount of dark matter we observe in the sky. Okay, so putting aside these two very well motivations, so what I want to focus today, the talk of today, is on the fact that these candidates are also testable with multiple and complementary strategies. So multiple, I just mean more than one, and I'm about to list the main ways to test this type of candidates. Complementary, as I will explain what follows, it means that each type of search is better at probing a specific range of mass or couplings. And so it's very important to push the effort along the different directions and combine the information we get. And that's also why we are concerned about how to combine them properly. So the three main channels to test the WIMP paradigm are all based on this type of diagram here and the crossing symmetry of this. So let's start from the case where we take the same diagram. So the same diagram today describes a dark matter annihilation in a region of the sky where we have a high dark matter density, like the center of our galaxy or some dwarf galaxy around the Milky Way. And so we aim at detecting the annihilation products of WIMP annihilations happening today. This is what is called indirect searches. Now, if we rotate this diagram by 90 degrees, this diagram describes elastic scattering between dark matter and, well, in this case, it must be some hadronic components, so quark or gluons. And we look for this process by looking for recoil energy in underground laboratory, where we look for the recoil of this scattering happening today on Earth in a very well-screened environment, of course, because the signal is very weak and we have to get rid of the background. Finally, if we rotate 90 more degrees this diagram, now we have a process with dark matter in the final state, and this process describes the production of WIMPs at collider, by colliding protons, for example, at the LHC. Of course, if all we do is produce WIMPs, we don't see anything in the detector because they just escape the detectors like neutrino. So we have to consider a process where we also produce something else, for example, a gluon from initial state radiation. And so this type of search is searching for events of one jet and missing energy which is due to the fact that the WIMP are not detected. And this is happening, and it's been happening in the last 10, 15 years. And there were impressive, by impressive results, I mean that the exclusion limits we get today are orders of magnitude improved with respect to the one from a few years ago. along the 3 channels. And the effort will continue in the next 5, 10 years, 20 years. And the limits will be pushed orders of magnitude more beyond the current one, and hopefully there will be a discovery. And the reason why I'm interested in comparing results from these different research strategies is that each one of them is probing dark matter couplings at different energy scales. So I would like to explain what I mean by this statement. So here I drew just the energy scales involved in the problem. In particular, you may recognize the 1 GeV, which is the scale of the mass of the proton, the mass of the Z boson, which I take as the scale where atomic symmetry is broken down to electromagnetic interactions, and then 10 TeV, which is roughly the scale of the collisions at the LHC. Now, on top of these known numbers, I also put 2 hypothetical numbers. One is the mass of the dark matter particle, mchi, and here is the mass of the mediator, which is an hypothetical particle mediating interaction between dark matter and us. Okay, so, of course, they don't have to be above the Z, they don't have to be in this hierarchy. The mediator can be lighter than dark matter. This is just for the purpose of illustration. But the point I would like to emphasize with this slide is that collisions at the LHC, of course, are probing dark matter couplings to the standard model at the energy of the LHC collision, of the energy of the partonic collision. So let's say order of 10 TeV. Of course, we have to be a bit more careful. Now, indirect searches, these are annihilation, no relativistic annihilation, because we know that dark matter today in the center of our galaxy is very relativistic. So the characteristic energy scale of this process is the mark of the dark matter itself. So it's the energy in the center of mass of the collision, which is twice mchi. So let's say order of mchi. Direct searches, on the other hand, there are probing very small recoil energy. So the right scale to describe this type of physics is the scale of nuclear physics, where the interaction of dark matter with quark gluons are matched onto interactions of dark matter with protons and neutrons, and then the hadronic matrix elements are computed by well-known techniques. But the question I want to address is how to bridge the gap between this scale, and the goal we'll be working on is to develop a general framework in such a way that we can connect these different energy scales automatically, meaning that we can produce general results that can be used by different models, and systematically, so the precision of our calculation can be systematically improved. And I would like to emphasize that this procedure is not optional, it's actually mandatory, because we know that between the mediator scale and the 1 GeV scale, if we talk about direct detection, there are standard model fields, which are active degrees of freedom. So at the top, there are all the quarks, the leptons, and we cannot ignore the effects of this particle, even if they are virtual. So they are not in the external legs of the process, but we cannot ignore the effect of this particle. So this is the outline for today. So first of all, I would like to say a few more words about the complementarity among WIMP searches and what are the mathematical tools we use to exploit this complementarity. Once we put information together in a plot, for example, what language do we use? Then I will focus on a specific yet broad class of models, which is the model of vector mediators, which are simply massive spin-1 particles mediating interaction between us and the dark matter. Then I will briefly review the framework to connect the LHC direct detection scale. I say briefly because this is based on a previous work I've done in collaboration with Massimiliano Procura, and I will just recall the main results. And then I would like to present the results of this recent study in collaboration with Bradley Kavanagh and Paolo Panci from Paris. And this is in preparation, but it will, as I said, I just checked that they posted it, so it will appear tomorrow. And this last part will be an application of the general, a specific application of the general formulas we developed roughly 1 year ago. Okay, so let's start from the complementarity. So, as I say, what I mean by complementarity? What I mean by complementarity is that each searches is better at probing some region of masses and coupling. So, I just would like to show you one example which I borrow from this no mass report on the WIMP complementarity. And this is a specific type of model of dark matter interacting with quarks. it doesn't matter the details of the model. All you have to know is that there is some operator describing this interaction. But on this plane, we have on the horizontal axis the mass of the dark matter, and on the vertical axis the sigma, the annihilation cross-section of dark matter to quarks final state, normalized to roughly 1 picobar, which is the one that we need in order to get a thermal rally. So this horizontal line corresponds to a sigma of 1 picobar, and then as we move, we have higher cross-section, smaller cross-section. Now, solid lines are current exclusion limits, and dashed lines are projected exclusion limits. So let's focus on the solid line. Okay, then the projected will just follow the same as I'm saying for the solid. So you see that collider, of course, is very good at probing small dark matter masses. Why? Because we don't require the dark matter to be present already, so we have to produce. And if it's lighter, it's actually better, because the collider has a finite energy in the center of mass. As we move on, it will be more difficult to produce dark matter from the just proton collision and fixed center of mass energy. On the other hand, indirect detection and direct detection, they do better than collider with some caveats about direct detection, but let's focus on the indirect detection line. They do better at probing higher masses because they don't have to produce dark matter particle. They rely upon the existence of the dark matter particle in the galaxy. So the dark matter particle is there already. We have just to wait that it annihilates or it scatters with the detector. And of course, at some point, since we measure rho, and rho is mass times the number density, if we increase the mass, the number density will go down, and then we lose sensitivity. And of course, something I should also say is that collider searches are not subject to astro uncertainties, unlike direct and indirect detection searches, where we need as an input the distribution of the dark matter in the galaxy or the velocity distribution of the dark matter in our galaxy. But so this is a nice example to show that we actually are probing all of this plane only after we combine these different searches. And so what is the language we use to summarize the results? For now, only exclusion bounds. In the future, hopefully, a discovery. These are counting experiments. They count events. And we have a background. In each case, in one case, it's an model background. In other cases, the astrophysical background. But in the end, we get limits on rates, which we would like to translate into limits on masses and couplings. So we need some mathematical framework to combine these informations. So the first one is just by assuming that the dark matter particle is the only beyond the standard model degree of freedom experimentally accessible. So that means that every particle that mediates the interaction between the dark matter and quarks, for example in this case, is heavy enough that its effects can be approximated by a point. This is like the Fermi theory of weak interactions. So we are just probing physics at energy scales so low compared to the mass of the mediator that we are just considering these effective operators. And you can come up with a list, as these people did in 2010, and you can classify the interaction according to the Lorentz structure of this vertex here. And once you specify this is the only information you need to specify, the Lorentz structure of this vertex. And this is a very economical description, because, for example, if we take the D5 operator, which is a vector current both on the dark matter and the quark side, this is a two-parameter space. The first parameter is the mass of the dark matter, and the other parameter is the suppression scale of this dimension 6 operator, which can be understood as the mass of the mediator, of course, assuming couplings over than 1 at these vertices. Otherwise, the rescaling is triggered. And you can present results from, for example, here it's an atlas analysis of ATV looking for monojet events in the plane M chi M star, which is the suppression scale of the operator. And you can draw exclusion limits on this plane. So you can compactly summarize the results in a single plane. So the obvious advantage of this description is that it's very compact because you only have three parameters. But it's also a problem because the limits here, you can see from this plot that we are putting limits on the mediator mass scale of roughly 1 TeV, and we have proton-proton collisions at 8 TeV. So it has been studied a lot, and it has been shown that for the discovery reach, for the limits, the reach on the limits we have, for LHC collisions, this approximation here to shrink this propagator to a point is not justified for LHC collisions. So we need to go beyond this description if we want to produce a plot like that in a consistent way. So the next step, of course, is to say, okay, the mediator particle is not just a point, but I'm accounting for the effects of the mediator particle, so I put the mediator particle in the spectrum. And as an example here, I have a theory where now I have the mediator A mu, spin 1 particle, that couples to axial current of quarks and dark matter. And once I interpret the LHC search, for the signal I use this diagram with the full propagator structure. So I'm sensitive to resonant effects, for example, of this propagator. If the dark matter mass is lighter than the resonant value, I can produce the mediator shell, and then I have an enhanced cross-section. And now it is possible to put limits on the mass of the dark matter particle and mass of the mediator in a consistent way. So here there is really no approximation about this propagator. Full mediator effects are taken into account. The problem is that the price to pay, I'm introducing 2 additional couplings here, which are dimensional coefficients, and in this plot they are fixed. But that's the only price to pay. And a nice thing we can do, this is a limit from collider. So for each dark matter mass, we have a limit on the mediator mass, and this limit can be translated into a limit for the cross-section between the nucleus and the dark matter particle. And now we can really combine in the same plane limits from collider and limits from direct reflection experiment. Now, this plot, the way I'm presenting it now, which is from this very recent analysis of Atlas, is not correct. So this line is wrong by a factor of 2. And the reason why it's wrong by a factor of 2 is because of the effects I'm about to talk about. And the key assumptions here to make this plot was just to make they just ignore the fact that the collisions at LHC are collisions at high energy, and the direct reflection experiments are physics at the nuclear scale. So if you forget about this energy gap and you do not connect the coupling in a proper way, this is what you get. Now, I'm about to show you how to connect the coupling in a proper way, and then I will come back in the end to this plot, and I will show you that there is a factor of 2 difference in this limit. So it's a 100% effect in the limit of the cross-section.
So you're just talking about moving coupling constants, right?
Running coupling constants.
Right,
Yeah. So I'm talking about, and I will explain with all the details. This is not considered for these models. Okay, so since in both examples I show you I had spin 1 currents, so I will discuss the framework we have worked on so far, because that's the one where, in my opinion, these effects are the most interesting one, and they were not studied before. And this is the case of vector mediators. So these are just some references of previous works. None of them included these effects, by the way, but this is just a simple parameterization for physics at LHC and the dark matter searches, direct and indirect. And this is the Lagrangian I'm going to use for the rest of my talk. So this is the theoretical framework. So it's a model where we have the standard model, Lagrangian, of course. And then we have 2 new degrees of freedom. The dark matter particle, which can be either a fermion or a scalar. So our analysis will work for both. The only assumption is that this particle is a dark matter singlet under the standard model gauge group. But the results I'm going to present are valid both for fermions and scalars. And then there is a spin 1 mediator. Here I only have the free part of the Lagrangian, just to introduce MV, which will be the mass of the mediator in my plots and in my results, both photos. And now let's get to the interesting part. So the interesting part is that the mediator B mu couples to spin 1 currents, and on one hand it couples to currents of dark matter particles, both scalar or fermions. And in the case of a scalar, we have this derivative with the antisymmetric combination, which is the only one that is a relevant matrix element. And in the case of a fermion dark matter, we can have both the axial current or vector current. Of course, if it's a Majorana fermion, we only have the axial current. We are keeping it as general. And finally, the mediator also couples to a current of standard model fermions. And here, I decided to couple the mediator to this current, where I'm using the actual standard model degrees of freedom with well-defined electroweak quantum numbers. So quark doublets, quark singlets, lepton doublet, lepton singlet. And this is because it has been shown in the past that if you, of course, I mean, I don't need to justify gauge invariant, but this is particularly important for dark matter searches because people before were coupling the mediator to a non-gauge invariant current of standard model fermion, which is not this expression. And by performing analysis for mono W scattering, for example, instead of mono jet, they found an enhancement of cross-section which was not physical. It was just an artifact that they were just using the wrong parameterization for the fields.
So what did they use? I mean, just give me an example.
Yeah, so they use, here I'm coupling to quark doublet and singlets. They use vector and axial current of quarks. So the vector and the axial couplings are related if you assume SU2 cross U1 invariant. So they were using some combination that was not gauge invariant and they found something that it was non-feasible. There was some excitement, but then the excitement went down. Okay, so just a simple counting. Here we have, the standard model has 5 different types of fermions, 3 quarks and 2 leptons, and they come in 3 generations. So we have 15 independent couplings in principle, and the framework we developed can be applied for any choice of this number. I will present results for benchmark cases, which I will describe, but I would like to emphasize that the examples I'm going to show are just because I want to present explicit results, but the framework we have can deal with any choice of these couplings, as well as any choice of dark matter couplings. Okay, so as we anticipated, the goal, what is the goal? The goal is to apply effective theory techniques to evaluate direct detection rates in this class of models. And I'm assuming this, since I'm using this Lagrangian to compare with LHC results, I'm assuming this Lagrangian with couplings evaluated at the scale of the LHC collisions, or at the scale of the mediator mass, which I'm taking comparable. And then I want to do a normalization group evolution of couplings down to the nuclear physics, scale of nuclear physics, and then compute direct detection rates consistently. So how do we do that? Okay, the reason, of course, is that the energy scale of the TU experiments is dramatically different. And I would like to present here for just 2 minutes a very well-known example from the standard model, which is the decay of the B meson. And the purpose of this example is not to teach you any B physics. It's just to draw an analogy, because then in the dark matter case we can really do a one-to-one comparison with what I'm saying in this slide and what we are actually doing for dark matter. So, the decay of B meson to d pi, all the dynamics comes in the matrix element. All we have to do is to compute the matrix element. Then the rest is kinematics. Once we know the matrix element, we know the decay width for the lifetime. And of course we know the full theory in this case. It's a standard model, unlike the case of dark matter. We know that the theory is a standard model, and we could use the standard model Lagrangian to evaluate this rate. But this is not the most convenient way, because in this matrix element there are 2 very different scales. One is the mass of the W, which appears in the Lagrangian, and W is the particle mediating the interaction. And the other one is the mass of the B, which is the center of mass energy in the decay rest frame, which is the energy available before the collision. And the way to actually compute this matrix element is to use effective theory techniques, which allows us to deal with one scale at a time in a systematic way. And what I mean is the following. So the first step is to integrate out every standard model states. So in this case, integrate out of the theory the W boson. So we go from a theory with quarks and W to a theory with only quarks, and the W effects are approximated to a point, which is fine because the energy we are interested in, which is the mass of the B, is way below the mass of the W. And this procedure gives me the so-called electroweak Hamiltonian, which is in Hamiltonian, it's a Lagrangian where we have contact interaction between quarks, these 4-point functions which I sketched here. And I wrote down here 2 operators. These 2 operators are different just for the color structure contraction of the quarks here. And the reason why I brought down both is because this matching here I'm describing at leading order is only switching on what I call the operator 1. So despite the fact that this process can be mediated by two different interactions, once I do the matching at the I scale, I only generate one, which is what I call one by convention. Now, the story to evolve the coupling to the mass of the W down to the mass of the B is a very well-known story. It's just doing the normalization group evolution of the couplings. And this is achieved by evaluating one-loop diagrams like this one with one gluon exchange between two quarks. And the effects I want to point out are these two effects here. The first one is that I started with the operator 1 switched on, and after the RGE evolution, the coefficient is affected. Before was 1, down here is 1.12, so it's a 10% effect. And the other effect is that despite the fact that I did not have the operator 2 switched on at the scale of the W, once I go to the scale of the B, this operator is induced by radiative effects. And so I end up with both at the scale of the mass of the B. And then once I have the Latoureux Hamiltonian with couplings evaluated at the scale MB, I have the Latoureux Hamiltonian at the right scale, and so I right scale to evaluate this hadronic matrix element where now I don't have any scale separation anymore, and I can work at the scale MB and evaluate this matrix element with
Can I ask a stupid question?
Yeah, sure.
Why is it a Hamiltonian and not a Lagrangian?
Oh, this is just the nomenclature. Don't ask me why. That's the way it's called in this.
Okay.
So this is minus L. So if you write the Lagrangian, it's minus this quantity here. It's just,
Good.
But I guess it's because it's using non-relativistic physics, so you can compute it. It's just a name. Okay, so these are the three-step procedure to evaluate the B lifetime. We first integrate out the mediator, we do the RG, and we compute the matrix element. The RG switch on new interactions, other than modifying the couplings of the old one. This is a very important point. Okay, now what is the analogy I want to draw? The analogy is that in the dark matter dissection we are doing exactly the same thing. The only difference is that we don't know the theory. In this case, we knew it's a standard model. Here we don't know what the theory is, but for each theory we can go through the same procedure, and we can integrate out the mediator. In the case of this talk, a spin-1 mediator. We can compute this effective interaction between standard model particles and dark matter. We get the coupling evaluated at the scale of the mediator, as before we were getting the ones eventually at the scale of the W. We do the RG, the same way we did that for the B. We end up with the couplings evaluated at the nuclear scale, and then eventually we compute the matrix element for dark matter elastic spectrum. So this is, as I will show you, is a lot of work. So why do we have to worry about these effects in a phase where we haven't discovered the dark matter yet? So you might wonder why, in the end, these effects are loop effects. So do I worry about loop effects in the pre-discovery phase? So there are two answers to this question. The first one is that, well, I'm just changing the size, this is the right thing to do. But of course, if these are only 1% corrections, it's not really a good argument. The favorite answer I have for this question is that the RG, one of the effects of the RG, as I show in the slide for the B decay, which is a known example in standard model, is that we generate new interactions through this RG procedure. So our ultimate goal is to evaluate matrix element for elastic scattering between dark matter and nuclei. And these matrix elements are extremely sensitive to the structure of the interaction between dark matter and quarks or gluons. For example, we talk about spin-independent cross-section. We talk about spin-dependent cross-section. We talk about velocity-suppressed interaction. So in the end, it is very important that even if we switch on a new interaction, and this new interaction is one loop suppressed, it could still be the dominant contribution to direct detection rate. So here I have an example, and this is just a description of a few examples that I will show in the following. Imagine that you have a theory where the mediator couples only, for example, only to leptons, or only to the top and the bottom. Or maybe he couples to light quarks, but he couples through the axial current, which is something that then gives a spin-dependent cross-section. So we would just say, oh, these cases, they give you a very small direct electron cross-section, I don't care. But this is not the right way to do that, because this is a statement made at the mediator mass scale, and if we want to generate the direct electron rate in this model, we have to carefully connect the two scales. And as I will show, it is very likely that we are going to induce through radiative correction unsuppressed interactions. And so I will show example of this case. And so this was known. There were explicit examples of cases like this. What we did in the paper, the one I wrote 1 year ago with Massimiliano Procura, was to do a general study for this type of spin-1 mediator. We did a full structure of this RGE evolution. And the way we do that for vector mediators is through these 3 steps. The first step, of course, we integrate out the mediator, as I said before. So this is now the massive spin-1 mediator case where we collapse the effect to a point. Then we do the RGE evolution, as I described before, and with a particular attention to the new interactions that are generated through operator mixing. And then, in the end, once we have the couplings evaluated at the nuclear scale, we can match the theory to theory of nucleons, and then we can evaluate the matrix elements with well-known techniques. And we have, before we started with this analysis, we had all the ingredients to put these informations together. Because first of all, integrating out the mediator is straightforward. It's the same way you integrate out the W or the Z in the Fermi theory for weak interaction. So you just generate a contact interaction between currents. Now, connecting this Lagrangian here at the mediator mass scale with the one at the nuclear scale, we derived the RGE equations for these spin-1 currents in this paper. So all we had to do was to solve the RGE equations. And finally, once we have the couplings at the nuclear scale, we can evaluate, we can match our theory of quark and gluons to a theory of nucleons, and then evaluate nuclear matrix elements by well-known techniques. For example, these 2 papers here, where everything can be done automatically. So, what I would like to describe briefly now, before I get to my results, is how we connect this contact interaction at the mediator mass scale with physics at the nuclear scale. And we do that through the RGE equations. Okay, so this was the topic of this paper here, and we divided the RGE evolution into 3 steps, because the first step, of course, is just to integrate out the mediator, which is a standard procedure, and to have a. So I would like to emphasize here that in the results I'm about to present, at the mediator mass scale, this current of standard model particles is only made of standard model fermions. So it's a current, spin-1 currents of standard model fermions. But in order to have a basis of operator which is closed under a normalization group, we also had to introduce this operator which is a current of X. And this operator will be very, very important, as I will show in the next slide. So we include this operator in the RGE study because even if you don't have here, you induce that through radiative corrections. And finally, this operator here, which is the derivative of the hypercharged field strength, it is there, it can be there, it's dimension 6, but it can always be redefined away by using the equation of motion of the hypercharged gauge field. So we did not include this operator, but we use consistently the equation of motion to account for its effects.
Did the RGE running change the relationship between this redundant operator and other operators?
So the RGE running will induce this operator, but then you can always redefine the one you induce by using the equation of motion, and you end up with this and this as well, because the X is charged on the upper charge. So as long as you include this and this, you are fine because it's a closed basis. So that's the beginning of the RGE evolution. So this is physics at mediator mass scale. We match, we make sure we have a basis, we control, and then we start the evolution. So we compute loop corrections and we see how these operators are induced through radiative corrections. And in the end, a very compact and elegant way to summarize this evolution is just to write down a vector C of couplings, which evolves according to this equation where gamma is a matrix called the anomalous dimension matrix. And these are just examples of loop diagrams that induce operators. So here, for example, you see that even if I don't have the X current, I induce that through loops. And here I have a diagram where you induce the redundant operator, but then you can always redefine a way by using the equation of motion. So that's the first type of RGE evolution. And we stop with this first part at the weak scale because we want to integrate out the standard model degrees of freedom that have a mass of the order of the weak scale, like the top, the Higgs, the Z, and the W. Now, once we do the weak scale matching, this is the most dangerous diagram at the weak scale. So here I have the X current, which is generated through loops. And I'm giving the X Q waves. And I have basically an effective vertex between the dark matter and the Z. And once I integrate out the Z, I attach fermions. And the Z couples to the vector current of fermions. So this is, at this point, like a fourth generation neutrino in the language of direct detection. So even if this coupling is suppressed by one loop, it is very dangerous because fourth generation neutrinos were excluded many years ago by direct detection. And of course, this is not the end of the story, but minor effects also arises once we RGE evolve the theory from the weak scale down to the nuclear scale, which is the last step. And again, this is described by this type of equations where you have a matrix summarizing the evolution. And also in this case, you have a redundant operator with the form. Yes?
So if you had more complicated Higgs sector, GW,
Okay.
whatever, I guess if you were in alignment and if you only one Higgs sector dev, would the other Higgs have any effect? I mean, obviously the most dangerous diagram knows about the standard model like Higgs, but there may be other diagrams involving other Higgs.
So I guess it depends where the other Higgs are in this picture. So if they are here, then definitely. In the alignment limit, so they are not heavy, right? They are a few hundred GeV.
Right.
I think if you're not, as long as you're not doing any Higgs loops, you could just use the Higgs.
But I am doing not in this diagram, but there are a few Higgs loops. But if you don't, so that's the question also about the UV complete model, because if the mediator does not couple to the Higgs at 3 level, these Higgs loops are Q-loop effects. And so we may argue that they are not relevant. But in a more general picture where the mediator couples to the Higgs as well, then these Higgs loops are dangerous, then the analysis must be extended. So that's an interesting further direction, I think, for extending the Higgs sector. So in this case, I'm just assuming the... Okay, so just to show that we actually did the calculation. So in each phase of the theory, the anomalous dimension matrix is a 16 times, you don't have to read it. That's not supposed to be right, just to show off in some sense. So the matrix element is, the anomalous dimension is a 16 times 16 matrix. And the reason why it's 16 is because I argued we have 15 coupling to quarks plus the X current, so it's 15 plus 1. And it's the sum of Q matrices that you can write like here. And so doing this RGE is tedious because you have to numerically solve this equation from here to here, match, and then solve this other equation from here to here. And that's what we did for the plots I'm about to show in the paper that will be appearing tomorrow. Now, just to guide the intuition, I would like to discuss in a very simplified way with a big warning sign what the main effects of this RGE evolution are. And we get within 50% the effects if we use this language. So it's not bad, but we did a proper job. This is just to, before I present the result, to just see what the main effects are. So imagine that you have a mediator V coupled to a vector current of standard model fermions. So the main contribution arises from this penguin type diagram where you have a photon exchange here. And you induce vector currents of light quarks, which are of the size of the electromagnetic loop. So electromagnetic because of the photon here. Okay, so if you start in the UV with a mediator that couples to a vector current of any fermion, so it could only be electron, let's say, only electrons, the RG will induce you only vector current of light quarks, and the size is small. So these effects are important, of course, only if you couple only to the top here, for example. If you couple only to the top, then you go down and then you find something which is sizable to the light quarks. But if you couple to the light quarks with the vector current in the first place, these are very small collections. Okay, so it depends what type of theories you're considering. Now, the most interesting example is when the mediator couples to the axial currents of some other fermions. The dominant diagram here is this Z exchange. And if you start with an axial current, you run down and you induce both vector and axial. Why? Because the Z coupled both to the vector and axial current. And now the size is as big as the Yukawa loop. So the relative weight of different fermions depends on what fermions you are considering. If you have a top here, this is a huge effect because the lambda of the top is large. So these are, because now I'm about to present explicit cases, so I just would like you to keep in mind that if the mediator couples to vector currents of fermions, we have an electromagnetic loop. If it couples to the axial current, we have a Yukawa loop. So that's.
So what lambda F is that now?
Oh, this is the fermion. Sorry, this is the one inside here, of course.
No, but the lambda, which coupling is that?
Oh, the Yukawa. This is the Yukawa.
So why in that diagram do you get a power?
So it's mass square in the loop, and then you get the Z mass, which is proportional to the X valve. And so it's mass of the fermion over the X valve, and so it's the Yukawa. In the alternative way, you can do the calculation in the unbroken phase, and then you have QX insertion on that, if the propagator is massless. So that's how you see it. Okay, so done. We have, and this is again the old paper. So we have a complete framework to develop. We develop a complete framework to connect the scale of LHC and direct detection through this RGE analysis. As I say, the equations to solve are a bit painful because there are 16 equations in each phase of the theory, and these equations feature running some model couplings. So we have to introduce also the running of some model couplings to be consistent. And for the results I'm about to show in the last 15 minutes, we did a full analysis. It is possible to understand the analysis in this approximate form, but tomorrow with the paper we are also releasing a public code that, very simple, can perform the running between actually any two energy scale in this plane. But if you give me the coupling to the mediator scale, the code will give you in 1 second the coupling at the scale, and this accounts for the full story. So accounting for these effects starting from tomorrow will be extremely simple. Okay.
So you use the standard model coupling running at one loop also? Or
yeah, it depends.
The GV scale.
No. So the running of the bottom, for example, that we use to 3 loop.
Okay.
The full.
Okay. So you use as
yeah. So
as much as you can.
We use known results for that.
Okay.
So we use whatever is known at the best precision. Yes. But the running in the dark sector is one loop. The one we did. Okay, so I would like to conclude with few examples because I've been talking about the general formulas. Now let's apply these general results, and I will show you explicit examples, and then I will conclude by showing why that LHC plot I showed you at the beginning is wrong by a factor of 2. Okay, so let's take theories where the mediator couples to a vector current of quarks. Okay, so this is the theory. It couples to a vector current of up and down in a flavor universal way. And this is, I put so much emphasis on gauge invariance before, but you can check that this is gauge invariant by choosing the coupling I defined before. So there is nothing inconsistent here. And for the dark matter case, I'm using the fermions, but it can be the scalar as well, and the results are similar. So let me just read the fermion for illustration. So in this first case, we have gamma mu on both dark matter and fermions. So very famously, this is a disaster for dark matter because it's a spin-independent rate which is enhanced by the size of the nucleon, by a squared, by the number of nucleons in the target. And in this plane where the dark matter mass is on the horizontal axis and the mediator mass is on the vertical axis, we see that lux, the last limits, they already exclude mediator above 10 TeV. So this plot shows you that this operator is bad. It shows you that RGE effects are small for this case because we have a vector current to the light quark in the first place. And so these 1% electromagnetic loop corrections are not doing much, and you cannot distinguish in the plot. The reason why I want to show this plot is because these limits for this operator are so good that even if we induce this operator at one loop, we are going to get very good limits, as I will show in a second. But before I get there, for completeness, let me also show the case where I have an axial current in the dark matter and a vector current to fermions. And again, RGE effects in this case are small, because as I argued before, the RGE effects, once we couple to vector current of fermions, they are only electromagnetic loops. So it's 1%, and they don't affect the rate substantially. Now, let's get to the interesting part. So, once the mediator couples to an axial current of quarks, which I take again flavor universal and equal for up and down, which is gauge invariant, electroweak gauge invariant. Here I show you this plot where I put the limits for gamma mu in the dark matter and gamma mu gamma 5 in the fermions in the same plane. Dark matter on the horizontal axis, the mass, and the mediator mass on the vertical axis. These lines are dashed. Before my lines were continuous. So the reason why I'm putting dashed lines here is because I start by showing you the limits without RGE effects. So that's what you get by ignoring everything I've been talking about today, which is what in general is done. And you see that the limits are extremely weak, of the order of 10 GeV for the mediator mass. And it's not easy, it's not hard to understand why. Because this operator is spin dependent, it's also suppressed by the momentum exchange, so it's very, very small rate. But now, if we include RGE effects, and we have seen that the fermion axial current mixes into the vector current, these are the limits we get. So it's a factor of 100 more in the mass of the mediator, which is a factor of 10 to the 8 in the cross section, because the cross section goes like 1 over the mass to the fourth. Sorry. To the square. And so this is probably the example where these effects are maximal, and you see that you get a factor of 100 improvement in a limit on a mass scale. Now we can do the same exercise for axial-axial case, which is the LHC case. So this is the case I showed you before where I want to argue that the plot is wrong. And in this case, axial-axial, again, with and without running. The difference here is a bit less pronounced than this plot here. But be careful because this is a logarithmic scale. And in this log scale, the limits are different by a factor of 2. Now, a factor of 2 in the mediator mass, once we translate that in the cross-section, is a factor of more than 10. Because it goes like 1 over mediator mass to the fourth, the cross-section for the detection. So I would like to translate this into the LHC plane and show you the impact. Before I do that, let me just say that these two examples have nothing to special, and we don't have to couple to light quarks at all. We can have models where the dark matter mass couples to leptons only, or he only couples to third generation fermions like top, bottom, and tau. And these are the limits you would get without running. No limits, right? If you couple to the leptons to the top, there is no interaction describing the direct detection. But of course, this is not a correct statement. You have to include what, despite being radiative correction, are the main source of the rate. And these are the limits you get. So again, they are, for these operators here, of the order of 1 TeV. So they're pretty good limits in the mediator mass. Okay, so let me get to the final part. So this is a plot we reproduced from the LHC analysis. here we have a contribution to the cross-section between dark matter and neutron. Here, dark matter and proton. So these are just two different target type, and this is because different experiments are more sensitive to scattering cross-section with neutron or protons according to the nuclear structure of the target. So we put both for completeness. And this is the plot that you would get once you translate LHC limit into direct detection limits by ignoring the running. And this is the one you get once you account for the running. So the RGE effects in this case, which is a case published by the Atlas collaboration, give you roughly a factor of 2 difference in the cross-section of spin-dependent scattering. So that's what it is. Okay, so let me conclude and discuss a bit what else needs to be done.
So could I just ask, coming back?
Yes.
The left-hand axis is spin independent? Or
No, sorry. They
spin
are
dependent.
They are both spin dependent.
Yeah, okay. And there's no mixing to the spin independent that occurs as a result of all this RGE?
Good question. So it turns out that there isn't, because this is the specific case discussed by the Atlas collaboration. So they discuss this model here. Gamma mu, gamma phi, gamma mu, gamma phi. And the RGE effect can only affect the fermion bilinear. So the dark matter will always be gamma mu, gamma phi. So there is no induced spin independent. And so, but this is true for this case. Of course, if they don't want to study this case, and the answer is because they told me we don't do this case because there is no direct detection. But there is not, if you don't, but there is. Okay. So if they did this, then your point would be very valid, and it would be the main source of. Okay. So let me conclude. So to summarize, the comparison between different thermal surgery is not always straightforward, and I've shown you few cases for the vector mediators where there are rates coming entirely from the RGE. There is the case of the LHC study where this effect is ignored, and it's a factor of 100% in the rate. And there are also models where you only couple leptons or third generation, and the RGE effects is the 100% contribution to the direct detection rates. Now, what about other type of mediators? So what I've been saying today is only about vector mediators. So let's take the case of a scalar with mass 750 GeV, just because of the recent excess in the diphoton events and the LHC. So we studied the possible dark matter in this paper here, in collaboration with Jordi De Vries and Paolo Panci, which we put shortly after the Christmas break. We studied possible dark matter candidates for this type of mediator. We did both the case of scalar and pseudoscalar. And the full story would deserve a separate talk. So I only want to say that in this type of models, where you have a scalar mediator, which is the only case where we have a substantial direct detection rates, if it's pseudoscalar, matrix elements are suppressed, and so it's not good for direct detection. The proper way to compute direct detection rates in these models and produce plots like these ones where we combine LHC and other searches with direct detection is to take the limits on the coupling at the 750 GeV events at LHC and then perform the RGE evolution between 750 GeV down to 1 GeV. And in this case, we found that these effects are a factor of 16 in the cross-section, or a factor of 4 in the amplitude, and then once you square it's a factor of 16. So even in this case, these effects are at least 1 order of magnitude on the direct detection rates. And of course, this is only one very specific example, but there is still a lot of work to do to quantify these effects for other type of models other than spin-1 mediators. Thank you.
Questions?
So is your did you have to compute all these one loop diagrams, or because there was a work by the San Diego people, right?
I know.
Manoir and Jenkins for the standard model running.
Yeah, but the standard model, there is no
So-
gauge singlet in the standard model, full gauge singlet.
Okay.
So
They extend.
we.
So that's you could not use this as a
No.
kind of way to extract. Okay. Clear.
I think in principle, the nuclear scale might be lower than 1 GeV, right? Depending on the nuclear that you're using for the scale.
Yeah, so what we are doing at nuclear scale is something. I mean, in the end, we have to match the theory between. So all I say, even if I didn't say that explicitly, but everything we're doing is a theory with dark matter interacting with quarks and gluons. But for spin 1, gluons are not really important. Now, at some point, we have to match the quark language to the nucleon language, proton and neutrons. And this is typically done at 1 GeV, but of course, there is some uncertainty in this procedure. And we take 1 GeV, but
Did you try to look at the RGE uncertainty that you get by, I don't know, taking the two loop running of
Yes.
versus the full 3
So we
loop or
didn't
something?
the Q loop in our case. So we
of the standard model, because I understand that probably since it's an integrated effect, it probably depends more on the high
Oh,
scale.
you see, in the standard model
But
couplings.
if you take the standard model couplings and you, I don't know,
Yeah,
you even
so-
take the one loop coupling versus the full to see what dependence you get.
What I did, I tried to change the RG scale, sorry, the matching scale.
Yeah, okay.
Yeah, with my code, so
Mhm.
same loop order, change it between 1 and 2 GeV,
Okay.
which
Yeah,
is the range
yeah,
which
for
is
it to
typically
go.
coded, and it's a very, very small effect. So.
Okay, because basically the effect is probably more
Yeah,
coming
it's,
from
it's
higher
a long,
scale, right?
it's a long
integrate-
range, exactly.
Okay.
So this
Okay.
specific of the neighborhood of 1 GeV is not a.
So it's quite robust.
Yes,
compared to
exactly.
the other before. Okay.
Okay. No more questions. Let's thank Francisco
Thank you.
again.